Okay, welcome everyone. This is session PS21, Computer Vision and Machine Learning for XR4, especially focusing on privacy and well-being. Good afternoon, my name is Gan Lee. I'm from University of South Australia. I will be chairing this session. And we have three conference papers in this session, while the session is 1 hour length. So we have a bit of room for a lot of questions and discussions. So the first presenter we have, the title of the paper is Preserving Personal Space, Differential Private Cybersickness Detection in Immersive Virtual Reality Environments. The authors are Ripan, Kumar, Kundu, and Khaza, Anuarul, Hoque from University of Missouri, Columbia. Our presenter today is Ripan Kumar Kundu. He's a PhD student in the Dependable Cyber Physical Systems Laboratory at the University of Missouri, Columbia. His research interests include the safety, security, and privacy issues in extended reality AI applications. Before we get started with his presentation, if those who are joining online through Zoom, please make sure you are muted. And also, if you have any questions, please post your questions onto the Discord channel, not the Zoom chat, so that we can monitor it, please. And if anyone joining here on site, please don't join on Zoom. Or if you do so, please make sure you mute your microphone and the speaker as well. Okay, thank you. Let's welcome the speaker. Thank you.
Hi, good noon. I am Ripan Kumar Kundu. I am a third-year PhD student at the University of Missouri, Columbia, and I will be presenting today our accepted paper. The title of our paper is Preserving Personal Space, Differentially Private Cybersickness Detection in Immersive Virtual Reality Environments. So let's get started. So here is my outline for today's presentation. So we'll talk a little bit of the motivation, then the research gaps, and our proposed solution, and then the experimental results. So as we know everyone like that, but VR headset is now increasingly applied for different application domains such as disaster management, military training, tourism and hospitality, industrial designing, healthcare, and many more. So what is the problem in today's VR headsets? So one of the problems is cybersickness, which is the significant obstacle for immersive VR experiences. The symptoms are basically the nausea, vomiting, facial pallor, salivation, or headache. So it's similar to the motion sickness, the symptoms, and there is a lot of theories in the literature, like to understand the cybersickness, or like sensory conflict theory, rest frame hypothesis theory, etc. So if you look at the first figure here, there is a session, VR session. There is a lady actually entered the VR session for some sort of experience, but suddenly she felt woozy. So one of the cyber sickness symptoms, and she felt severe cyber sickness that she left the simulation as well. And if you look at the right-hand side figure, that's the biggest news from the last year, that US Congress actually hauled $400 million order to purchase from the Microsoft HoloLens. And the problem, they find that most of the user, like the military, they feel severe cyber sickness, almost 80%. So that means cyber sickness is major problem still now. And then we are talking about the cyber sickness. Then what is the problem with the privacy? So as the name suggests, like the privacy means like that individual or the personal information cannot be leaked. And as we know, like that eye tracking data actually contain a lot of information. So for instance, when you immerse in a virtual environment where we look, how we react, then we can actually leak the privacy. If you look at the figure here, there is a VR user is trying to, in the metaverse, and look at some sort of billboard. Maybe he attracted some sort of drinks, specific drinks, and if his privacy is leaked, and for instance, like if he get the next day some sort of mail like that, hey, you are interested in some sort of specific drinks, that means the user privacy is leaked, and that can be different way. For instance, the attacker maybe, or the adversary can post it in some sort of social media and do some sort of harassment. So that's mean the privacy is a major problem in the VR. Then there is a lot of previous work that actually using for cyber sickness. If you look at the literature broadly, the cyber sickness actually divided into two categories. One is subjective and objective measurement-based cyber sickness, and one is machine learning and deep learning-based cyber sickness. Since subjective and objective measurement-based cyber sickness give not us the real-time or not real-time cyber sickness measurement during the immersion. So that's why researcher came like we can using a lot of machine learning and deep learning model to give the automated cyber sickness prediction, which give us the real-time cyber sickness. Then the problem is like that, as we know like that nowadays machine learning and deep learning model can actually learn a lot of information when the training from the publicly available data. For instance, like if we train a cyber sickness prediction model from a publicly available data sets, then we can actually encode the private information of the user, where they have this content, the different cyber sickness label on that data set. That means there is no, this kind of model actually leak the weird user privacy. If there is, if the adversary can take any intention. So, and then there is no formal privacy guarantee in state-of-the-art cyber sickness detection. So there is some work in the VR privacy. It's not specific in the cyber sickness domain, but there is some common attack is called re-identification attack in VR privacy. Why the re-identification attack? So there is a thing like that. We can simply de-anonymize the data set. For instance, we can remove the personal information of the user, like their age, gender, and then you can release the data set. But the Netflix find like that, the de-anonymization, the data cannot provide the privacy. So there is a challenge, Netflix challenge, I think few years back, they actually find some sort of linking with the Netflix dataset with the ambient rating dataset, and then they can actually leak the user privacy. And this is similar, same thing is going for the VR headset. Like since we are actually releasing our data sets, there's contain a lot of information, though we are doing some sort of de-anonymization, but there is a possibility that this anonymization cannot actually give us the privacy protection. And therefore, there is a lot of privacy guarantee protect in the VR. For instance, like differential privacy, some Kalido-based privacy mechanism. But the problem is most of these privacy guarantee actually provide in the sample level. So what they did like that, before releasing the dataset, they add some sort of noise and release the dataset. But think as a VR, because as we know like that, VR eye tracking data is a noisy source of information. If we add a noise, external noise to preserve the privacy, that's when you actually ruin your user experience. So that's mean when we trained a model for better prediction or accurate prediction, that's kind of model actually give not good accurate prediction, and that actually, this data set actually not give us actual privacy protection as well. And since we know like that machine learning and deep learning based cyber sickness prediction model or any kind of model can actually encode the user private information, and it then adversary can actually leak the privacy. So that's our contribution comes. We actually look at like that how one of the known attack is called membership private inference attack. Can be applied machine learning and deep learning based cyber sickness prediction model, and we can actually leak the privacy of the user, and we actually provide a solution for that. So then we come with like that, we have provide 4 private cyber sickness prediction model. One is LSTM, one is GRU, one is CNN, and one is the MLP. And our privacy achieved here is by epsilon differential privacy. During the cyber sickness training model, this meaning like that, both the data set and model both are private. And we actually look at like this, since the differential privacy has a problem with the utility, like when you add more noise, that's when you have actually lose your utility. That's actually hampering your prediction accuracy. So we actually look at that, how can we actually provide the privacy as well, and how we actually give the better utility, since we need a good cyber sickness prediction as well. And this is actually state-of-the-art applying, where they actually apply the sample level. In our contrast, we apply both model and sample levels. So if you look at that, the membership inference attacks from the figure here. So membership inference attack is just something that's actually identified if the individual user data actually used for the training for some sort of cyber sickness prediction model. And the main difference between the de-identification attack and membership inference attack is that you can linking the both dataset and reload and identify using the information. But in contrast, the MIA actually, we can find this where the specific user data is using for training the cybersecurity prediction model. So then the adversary can train a model, and then he can actually leak the privacy or identify the user, which user data set actually trained for the cybersecurity prediction model. And this is very highly relevant to the application like cybersecurity prediction model, where user data is using for building the model for real-time prediction. And if there is a membership inference attack applied, then you can actually leak the privacy which user data actually using for cybersecurity prediction model built. So that's our threat model. So the main goal is the attacker is to determine the individual instance, like the user data is the part of the data set or not. And the attack scenario, you look at the figure here, like so is a typical way, like we can have some public data set, we can train a machine learning or deep learning model, and then we have a real-time streaming data. So we have a trained cybersecurity prediction model, and then the adversary have access both the prediction model and the data, and then what he did like that, he can train an attack model and find the classification prediction. So if this attack model is successful, then he can actually query the model, and he can identify the user. If he's giving this 0, then means the data samples or the user is not in the training part. If he's identified as a 1, that means the user is in the training part. So that's mean, like, when he identified the sample, that's when he actually identified the user's cybersecurity level. Maybe do some sort of multiple query, and he find like that the specific user have always high cybersecurity levels. That means the user privacy is leaked. So that's why our proposed solution here. So what we do like that, we first build a non-private model, typical cybersecurity prediction model, and then take this model and do privatization. So in our privatization, we take the non-private model, and then we apply the DPHDD, differentially private stochastic gradient descent method. So it's basically similar to the HDD method, but what we did like that, before we compute the loss, we actually clip the gradients and add the noise here. So in our here we're using the Gaussian noise, and then we actually do some privacy accounting techniques, since, as we mentioned before, like that differential privacy is a problem with the utility. So we have to maintain the high privacy. At the meantime, we have to need for a better privacy utility as well. So mention that user have a privacy. At the meantime, the model actually giving a good prediction accuracy as well. So this is our method. So we first apply the differentially private stochastic gradient descent, and we modify the typical SGD algorithm, and then make differential privacy. And then we actually apply the moment accountant technique. So we can look at here, we first compute the gradients, and then we apply DPHDD method, where we actually adding the noise. In our case, we adding the Gaussian noise, and we actually do multiple iterations, similar way like traditional machine deep learning model trained. So for the evaluation, we actually using 2 datasets. One is the gameplay dataset with 35 participants, and one is simulation 2021 datasets with 30 participants. So we look at like here, like since we taking 2 example datasets because here, so we look at like that's this kind of a categorical feature, like where user information actually here, like for instance, like user position, user gender, user profile. That's actually the binary information, like it's male, female, or and we take some sort of data set, like since we have claimed that eye tracking data actually leak a lot of information or contain a lot of information. That's why we're using the data set simulation 2021 had actually contain eye tracking, head tracking, and physiological data set. And we first, our results, we look at like how the non-private and private model works. So there is no, first of all, we have no attacks or anything. So we have evaluated 4 models. We can see like that when we have a higher privacy, we have a low privacy, but with higher privacy budget. So we can see like that we have almost similar accuracy for the both private and non-private model. But when we try to get higher privacy, but we say like it's almost equal, it's almost 89% for the LST model. And both of these model, we find like that LST model actually get higher performance better than other GRU, CNN, and MLP model. Then we evaluate our system, we apply the membership inference attacks as mentioned earlier. So we look at like that, we calculate apply for both non-private and private model, and you can see like that when we apply for the non-private model, you can see like that for the simulation data set, we almost reduce the attack success rate is 34%, and for the same thing for the gameplay data set 42%. And we also calculate other metrics as well, like AOC score, and we also show like how the non-private and private model work for the AOC score as well. So this is for the both two data set. So then we actually do some privacy utility trade-off, because as I mentioned earlier, like privacy is always, when we apply differential privacy, there is always the trade-off between the accuracy. In our case, the utilities mean the accuracy. So we can look at how I increase the privacy budget, how much my accuracy is going. So we can see like that when you have a low privacy budget, we have a lower accuracy, but when you add the privacy, it's almost going similar. And if you look at for our private LST model, actually have almost 91% accuracy. And since we have for the evaluation, another evaluation, we look at since we are adding the noise. So if we adding the noise, more noise, how much are my utilities impact? So we take 4 models and we adding the noise from 1 to 2. This is the different noise levels, and you can see like that after 1.2 adding noise, when you add more noise, its accuracy slightly drop. But still, LST model is performing better than other 3 models. And this is the things like that we mentioned before earlier, like that. Okay, so we say like that since we have different fusion, different type of feature. For instance, gameplay data set we have like categorical and continuous feature, and eye tracking data we have different eye tracking, head tracking data. We look at like that how this privacy is leaking when we're fusing the data, and we find like that when we have like the simulation to the data set, we can say when we fusing for the eye tracking data, we almost getting leak higher privacy. At the meantime, we have the utility trade-off. So eye tracking is more vulnerable for attacking and leak a lot of information. Similar thing like we have like the gameplay data set, we have categorical and continuous feature, but when we have a categorical feature, we have higher privacy leak, and it seems we have a better prediction. So the reason is like categorical feature actually basically your different user attribute, like user profile, user genre, maybe age, gender, and that's actually contain a lot of information. And in conclusion, so we propose a differential privacy cybersickness prediction model, and which actually give a higher, which provide the higher privacy at the meantime better utility. Our DP method significantly reduce the attack success rate. And in the future, since we are actually do the data set and do in the real user study, so we are planning to deploy this method in the realistic VR headset and do user study and see how the user actually give the feedback. And last of all, I used this is a reference. And last of all, I to thank our sponsor, National Science Foundation and Army Research Lab for giving us the opportunity for this project. Thank you.
Thank you. Is there any questions from the audience?
Yeah, nice presentation. So I have one question I was trying to understand. So what if the attacker has access to the anonymized data, right? So they don't know that which data contains to which user. So there are millions of eye tracking data could be coming from their like same pattern but from different user. So even if I know the classifications, how would I know the identity of the user? Because the same pattern could be, or the same classification could be across multiple users, right?
Yeah, that's a good question. So for instance, like so when we release the data sets, that's when we have to release the cybersickness level as well, yeah, for the prediction. For instance, like the attacker actually querying multiple times, and multiple times he get the high cybersickness level, and he's giving some sort of probabilities. That's mean like the attacker have high chance to actually identify that user have this cybersickness probability. Since he have the level. With the sample, you have the level, for instance, the high, low, or medium. And seems like an application, for instance, where there is a real-time streaming data, and the same user actually using the data, and sometimes for better training the model, for better accuracy and something like that, we have to retrain the model. So that's mean that user data already trained with that model. And if the user in the same application and using the application, that's mean his data can be leaked, is identified. Am I correct?
there are actually two different attacks he talked about, re-identification attack and membership inference attack. So I think the re-identification attack, Brandon worked a lot on that one. In my opinion, I mean, re-identification attack is way more practical. However, the constraint that re-identification attack has, you need two data sets. One data set that does not have any identifier, the second data set might have some identifier, then you do the linkage. That's why it's also known as linkage attack. Yeah. However, in membership inference attack, it's way simpler. For instance, all you need to know is if Rifat's data was used to train the Cybersickness model or not. It will give me the answer yes or no. If it gives me the answer yes with the label, then it's easy to understand that, hey, probably his data was used for training the Cybersickness model. Now, it might sound harmless, but there are many cases it is not. For example, think about an ASD student, right, who has an ASD syndrome. Now, if I try to find, hey, if this student's data was used to train the Cybersickness model for special education or not, then you can actually leak that information and start doing a social harassment. And we actually have some collaboration with our ASD. There are actually a department who works with ASD children, and they are using a virtual reality learning environment. So we are actually trying to attack the real data sets after this one and see if we can do leaking of the information. So to me, it seems like MIA has more flexibility, and it's also very practical for VR. Unfortunately, we didn't find anyone who actually worked on this, so we picked this idea.
Thank you very much. Let's thank the speaker again. Thank you. If you have any more follow-up questions, please feel free to post them onto the discussion forum on Discord. The second speaker today is Qidi Wang. The title of the paper is Cross-Domain Gender Identification Using VR Tracking Data. The authors are Qidi Wang, Alec from University of Central Florida, and also Nayan Chawla and Ryan McMahan from Virginia Tech. So the paper will be presented by Qidi Wang. Qidi Wang is a undergraduate student in the Department of Computer Science at the University of Central Florida. Her research interests include virtual reality and machine learning. So let's welcome the presenter. Thank you.
Hello, thank you for coming. My name is Qidi Wang, and I'm an undergraduate researcher at the University of Central Florida. Today I'll be presenting my paper titled Cross-Domain Gender Identification Using VR Tracking Data, and my co-authors are Alec, Nayan Chawla, and Dr. Ryan McMahan. So to start out with some introductory background information, we know that extended reality systems, including augmented and virtual reality devices, track motion data, and this has been found to be highly indicative of both personal identity and users' attributes. Prior researchers in this field have conducted machine learning experiments that have been task-specific and domain-specific. Our primary contribution is one of the first cross-domain investigations in which we conduct machine learning experiments trained on models, trained on the assembly domain, tested on the gaming domain, in which we use different data sets with different participant pools. Now, by nature of us conducting cross-domain experiments, we are using data sets with completely different participants, and thus we are unable to investigate personal identifiability. However, we have found that we can conduct an investigation into users' attributes, and we selected gender as our research topic for various reasons. One of them being that prior researchers have found that males and females demonstrate significant differences that are pertinent to virtual reality, and these include in simulator sickness, color perception, wayfinding, spatial presence, and empathy. Identifying the gender of a VR user has various benefits, and one of these is providing customized experiences. So for example, this may look like providing the navigation teleportation technique to minimize simulator sickness in women and increasing illumination to aid color perception in men. Our other contributions include an in-depth exploration of the device combination and spatial representations effects on our machine learning model accuracies, and we make our code open source on GitHub for the sake of future researchers to replicate our work or build upon it. So for a quick overview of our related work, we see here that many researchers have investigated task-specific machine learning experiments. And this is when models are trained and tested on users performing the same task in the same domain. Many have also investigated domain-specific experiments in which models are trained and tested on different tasks from the same domain. At the very bottom here, we see our paper in which we conduct experiments that are cross-domain. These are trained on users performing different tasks from different domains. We also observe here that while many have investigated personal identifiability, fewer have targeted identifying gender as the user attribute. And finally, we see that our in-depth device combination exploration builds upon an already rich body of work in the field. So our research questions are the following. We wish to understand how these factors affect gender identifiability. First of all, how do cross-domain experiments compare to domain-specific experiments, and is one more predictive than the other? Secondly, we wish to understand the effect of the training domain. This suddenly becomes a pertinent question because our training and testing domains are different, and our trained tests subsets are split by domain for the sake of ecological validity. We wish to understand the effect of VR tracking device combinations, spatial representations, and machine learning algorithm used upon the accuracies, as well as which features are the most indicative for our models. Here, device combinations include the headset, left and right controllers, and spatial representations include position, quaternion Euler, and 6D rotation representations. The machine learning algorithms we selected were k-nearest neighbors, random forest, and gradient boosting machine, and we selected these based on their high performance in similar works. So for our assembly domain, we utilized the FAST dataset by Moore et al., and here users were guided by interaction cues to assemble two different tube structures, structure A and structure B. This led to a very intuitive subset breakdown in which build A corresponded to subset A and build B to subset B. The researchers collected data from the headset, right and left-hand controllers, as well as position and orientation data for each. The participant data available to us were that of 56 males and 50 females. For the gaming domain, we used the Who is Alex dataset by Rack et al. And here the researchers they gathered data from users playing different levels from the popular game Half-Life Alyx. Level 1 corresponded to subset A, and level 3 of the game corresponded to subset B. While the researchers collected data from many devices, we focused only on the headset and controllers for consistency. In addition, they collected position and quaternion data, which we then converted to Euler and 6D representations. The participant data available to us were that of 33 males and 30 females for subset A, and 34 males and 28 females for subset B. Now, before I move on, I wanted to quickly touch on rotation representations. The Euler and the quaternions should look familiar to you because they're commonly used in the field. However, the 6D representation may look new. We selected the 6D representation as part of our investigation because prior work has shown that they are sometimes more indicative in deep learning contexts than Euler and quaternions, which are the standard. You see here that in this standard 4x4 transformation matrix, the highlighted values are the 6 values used in order to create the 6D representation. So in order to prepare our data for machine learning experiments, we had to pre-process it with this pipeline. We started out with the raw participant data, typically collected at 90 frames per second. We aggregated them into 1 second intervals and then calculated 5 summary statistics for these intervals. These included the maximum, the median, the minimum, mean, and standard deviation. We then used this to compute the n-dimensional vector, which is fed into as the input to our machine learning models. And n is the product of the 5 statistics by the number of spatial features by the number of devices we are examining. So for a high-level overview of the specific experiments we conducted, We examined both domain-specific and cross-domain gender identification for the purposes of comparison. We conducted 588 domain-specific experiments and 1,176 cross-domain experiments, for a total of 1,764. This is also why we chose not to optimize hyperparameters for our research, as this would have led to a computational explosion in the number of experiments we would have had to conduct. Thus, this is an area for future work. So our domain-specific machine learning pipeline is the following. We start out with a subset of data, train one of our 3 models, and then we test it with the other subset from within the same domain. We then collect our accuracy F1 and precision recall scores, which we present in more detail in the supplemental materials of our paper. Now, our cross-domain machine learning pipeline is very similar. We start out with the subsets and train the models as before, but this time we test it with a subset from the opposite domain. And in a similar manner, we gathered the 4 evaluation metric scores in order to compare our results. So here we present the results of our experiments. The following tables are the average scores for each kind of experiment, and they are presented in such a way that the 7 device combinations are the rows and 7 spatial representations are the columns. The color coding here corresponds to the accuracies of the scores, where scores referring closer to the 50% mark they are red, and the scores closer to 100% are green, because this is a binary classification problem. We see here that for the assembly domain, everything in the first 4 rows perform well as indicative features for the sake of gender identification. For the gaming domain, this is a subset of the previous features in which the headset and position are the most indicative of gender. Now, before I move on to our cross-domain results, I wanted to point out that the k-nearest neighbors model did not perform well in cross-domain experiments. And this makes sense because k-nearest neighbors is intrinsically based upon distance calculations. Naturally, this does not translate well across domains. We see here that many of the scores hover around the 50% threshold, and some of them are even suboptimal. Thus, given this, we discourage researchers from using the k-nearest neighbors model in similar experiments in the future. So for our cross-domain results, we see that models trained upon the assembly domain and tested on the gaming domain shows a stark contrast in the effectiveness of using head position and those that do not. Similarly, with models trained on gaming and tested on assembly, we see a similar subset of features, although it is slightly smaller because the position and Euler spatial representation did not perform as well here. These tables help us understand 2 things about cross-domain gender identification. Number 1, that the training domain does make a difference in terms of accuracies of the scores, as well as the specific subsets of features that are indicative. We also observe that cross-domain gender identification is more challenging than domain-specific identification, as the lowest scores in the tables here are worse than the lowest scores in the domain-specific tables presented previously. So the conclusions of our study are that cross-domain gender identification is more challenging. We also found that head position is extremely important for gender identification, and we conjecture that this has to do with the head's y-axis correlating to the user's height. We found that the training domains do matter, and depending on what kind of results and experiments you're trying to conduct, it may be better to train upon the assembly domain, or it may be better to train upon the gaming domain. We also found that the k-nearest neighbors model for cross-domain experiments performs poorly, and this affects what models researchers choose in the future. Now, some limitations of our work are that we only examined 2 domains, gaming and assembly, when there are many more domains in the virtual reality field that we can examine. We also did not look at individual input features, rather we looked at combinations of features. And finally, we used 3 simple machine learning model techniques, but there are many out there that can be used as well, and we encourage researchers to investigate all of these for future work for the sake of the privacy and security implications, as well as the affordances of customized virtual reality experiences for every user in the future. Thank you for your time.
Thank you. Is there any questions from the audience? you're thinking, probably I will ask a question. So thank you for the presentation. Sounds like your future work is trying to expand this into different domains, and obviously there could be many different domains. Do you have any directions or ideas about how would you choose a domain that would be more effective or more useful in the future?
Yeah, thank you for your question. So as we know that there are many assembly virtual reality applications out there, as well as gaming. Virtual reality is commonly known for gaming. However, some domains I think that would be interesting to investigate are training simulations. For example, there is one data set I know of in which users learn how to troubleshoot a robotic surgeon, and that would be a very effective domain to investigate, as virtual reality has such a important place in the world as providing these training simulations, when doing so in real life might be dangerous or otherwise expensive and infeasible. And so that's the one that comes to mind most, but there are, as you know, many other domains that we can investigate. So the area for future work is definitely very broad, and I'm excited to see what research comes of this in the future.
Thank you. Any other questions from the audience?
So you said in discussion section, head position is related with the gender identification.
Mm-hmm.
So can you explain more like how they are related? Like for gaming, usually how head position can use to recognize the genders?
Yes, thank you for your question. So because of the scope of our research, we did not do an in-depth exploration of specifically why head position is so indicative of gender. However, we do hypothesize that this has to do with height. For example, males tend to be taller than females, as we know from life experience. And so typically this may be the feature that stands out to the machine learning model. Might be how it discovers, oh, this is very indicative of the gender of the user. But of course, there are exceptions. And so I would say another area for future work is to conduct a specific examination into all of the axes, the position XYZ of head position, the rotation, Quaternion Euler 6D, and all the corresponding spatial features there in order to understand why exactly head position is so indicative.
Maybe I'll just ask one more quick question. So, so in your study, you've mainly included 2 domains, so that was why probably you didn't really have a case of training them in a multi-domain. But maybe in the future, if you have more than 2 domains, would you consider training on a multi-domain and then trying to apply it to the other domain that was not included in there? Would that be something that be interesting in the future?
Yeah, that is an excellent suggestion. I can see this carried out in different ways. So we could train upon one domain, test it on 2. We could train it on 2 and test it on 1. We could evaluate all the different combinations and permutations of these training and testing experiments. And that's what I love so much about machine learning, is that they're so versatile. And depending on the different data that we feed into it, we can get very different results, as we have shown here. And so my only concern with training with 2 domains is that because the domains are so unique to the context, the machine learning model, we want to prevent it from being confused in terms of what domain it is looking at and what dimensions we are looking at in terms of the motion tracking data. So if I were to conduct this experiment that you're proposing tomorrow, what I would likely do is I would train upon 1 and then test on 1 individually, but explore all the possible combinations. And then from that, I would go and do further investigations.
Okay, thank you. Let's thank the presenter again. Thank you.
Thank you.
Okay, the third and the last paper is Mazed and Confused, a data set of cybersickness, working memory, mental load, physical load, and attention during a real walking task in VR. The authors are Jyotirmay, Setu, Jyotirmay, Ripan, Kumar, Kundu, Giesbrecht, Tobias, Höllerer, Khaza, Anuarul, and Hoque. And the paper will be presented by Jyotirmay Setu. He is a PhD student in the Department of Computer Science at University of Texas at San Antonio. His research interests include predicting and mitigating cybersickness and cognitive load in virtual reality environment. So let's welcome the presenter, please. Thank you.
Hello everyone, good morning. So today I'll be presenting our paper on a cybersickness dataset. So this is also a dataset of cognitive load as well. So as you probably know, the modern day VR application, they have real walking based navigation now. And most of the dataset we have today of cybersickness that doesn't actually include locomotion that much, or maybe restricted by only teleportation based locomotion. But in this particular data set, we wanted to examine the particular impact of real walking-based navigation on cybersickness. One other aspect to consider is cognitive load, because most of the modern day VR application is getting complex, and it actually requires you to perform multiple cognitive tasks that can be demanding on your, that can be physically demanding, mentally demanding, and it can be challenging for your working memory and attention as well. So through this data set, we actually want to examine the impact of cybersickness on cognitive load and vice versa. So if performing too many cognitive tasks will make you sick or not. So let's take firefighter training simulation for an example. So you are navigating through virtual fire, that is real walking-based navigation. You are trying to find survivors that requires focus and attention, and you are trying to remember a safe exit that actually requires working memory. So to replicate a perfectly real-world simulation, we present to you mesh dataset. So our contribution here is the open Nobel dataset, VR walking, that actually collects levels for cybersickness and cognitive load. We perform some preliminary data analysis that actually suggests that there is a connection between cognitive load and cybersickness, and we did train some deep learning models, very straightforward deep learning models, to test out the utility of the cybersickness dataset, how well it performs in terms as a cybersickness dataset. And we chose those deep learning model to do further shape analysis to figure out what type of feature were important in terms of cybersickness prediction. So these are the equipments, the HTC Vive Pro Eye that was used because it comes integrated with eye tracking and head tracking. The new lock sensors are wireless modular sensor. They were used for not restricting the participant to actually walk around. So it is perfectly usable for real walking-based navigation. So before the actual session began, there was a tutorial session. It was a brief 1-minute session. We actually described the task. There are 2 tasks, one relating to the working memory, another to the attention task. We checked the equipment and we did the eye tracking calibration, because you need the eye tracking calibration because eyes are so different for every participant. So this is actually how the overview of the whole mesh session looks like. So at the beginning, the participant actually get the initial 5-digit sequence. This relates to their working memory task, and they also receive a keyword that relates to their attention task. So they actually navigated the maze for 15 minutes, and the navigation doesn't stop. They perform 2 separate tasks, the attention task and the Q&A session while walking. So the attention task, that actually went on for 30 seconds and followed by a Q&A session of 30 seconds. So the attention task, we actually fed them a word stream of 5 words, alpha, bravo, Charlie, delta, and echo. And if you remember, we gave them a keyword at the beginning. So they had to remember the keyword, and they have to press the button on the joystick if it was not the keyword, and skip pressing if it was the keyword. So this is how we calculated the attention metrics and level the multimodal data set. So basically, if it was the keyword, they didn't press, they skipped it, and we considered that as a mistake if they pressed on the keyword, and the percentile was calculated to level the data set. So 80% was the accuracy at this particular scenario. We also calculated the reaction time, so the time between them hearing the sound and them pressing the joystick button. That was also used to level the data. And the Q&A session, they actually answered 3 separate questions relating to their physical load, mental load, and FMS, this is cybersickness. And they also repeated back the initial 5-digit number we give them. And we also give them a randomly generated new 5-digit sequence to repeat back at another Q&A session. So this is how the working memory load task actually was calculated. So we also calculated this as a accuracy percentile. So the index and the number has to match. So the 60% was the accuracy at this particular scenario. And this was also used to label the multimodal dataset that we collected. So this was basically what the maze collection simulation actually looks like. Over there, that's the top view of the maze. It was randomly generated every time. This was
Alpha.
the participant navigating. That's the for the attention task. You see the keyword.
Charlie.
And they press during this session.
Alpha.
After this session, there will be a Q&A session.
Alpha. Please answer the question from a scale of 1 to 10. How sick do you feel? How physically demanding is this task? How mentally demanding is this task? What were the last 5 digits stated? Here are your next 5 digits.
So the next 5 digits would be repeated back in the next Q&A session. So this is the data we collected. Data relating to cognitive load would be attention, and we collected 2 different matrices: correct button press and reaction time. The working memory load was also a percentile. The physical load and mental load was collected during the Q&A session, and the NASA TLX were administered after the session. And for cybersickness, we collected the fast motion scale FMS score, and that was collected during the Q&A session as well. And the SSQ was both pre and post session. So for the objective measures, we collected eye tracking, head tracking. They're both at 60 hertz. And the physical reading was heart rate and GSR. They were collected at 10 hertz. And the VR images were collected at a 60 frame per second ratio, probably. So the VR images was basically the left eye view, VR view, that was collected using OBS Studio. And based on our preliminary data analysis, we saw that FMS tends to grow over time, and so does physical load, mental load. And we had an hypothesis that biophysiological reading would grow over time as well with FMS and physical load. We didn't find any correlation between the HR, but upon examining the first 30-second GSR and the last 30-second GSR, we did find a significant difference there. And we actually grouped the participant based on their FMS score. It was a median split. So the grouping on sick versus non-sick, and we examined those data, and we found out that there is a significant difference between their physical demand and annoyance questionnaire that comes from the NASA TLX, and also their working memory task performance was also significantly different in between the sick and non-sick group. And for checking the utility, we also did the cybersickness classification utilizing 3 very basic models, LSTM, GRU, and MLP. And we also had a vision of performing a shape analysis to find the most important features out of this. So this is what the results look like. We got around 95% of accuracy with GRU and LSTM in 3-class classification for cybersickness. So this particular data set is perfectly usable for making a cybersickness prediction model or maybe fine-tuning another pre-trained model. And so we chose the particular models, LSTM and GRU, because they're well suited for time series, and MLP was chosen because we had another vision of uploading lightweight models to standalone VR HMDs. So MLP has much lower number of parameters, so it is a perfect fit for doing those sort of stuff. And the next motivation of using a straightforward DL model was to perform shape analysis, and the shape analysis was conducted because we wanted to find out the dominant features for cybersickness classification. And the results are surprising. We found out that biophysiological reading like GSR and heart rate are some of the dominant feature, and we didn't find any head tracking feature in the top dominant list. We only found the eye tracking feature, and especially the diameter information, the right diameter and the left diameter is some of the most dominant feature. So as I said, there is no head tracking feature in the top dominant list, and eye tracking and biophysiological readings are the only dominant feature. Although it is difficult to collect heart rate and GSR, but it is a perfectly good modality to predict cybersickness. For future work, we still haven't used some of the modalities that we collect, like the VR images or some of the levels that we collected, like the cognitive load levels. We want to work on that for cognitive load prediction using our dataset. We also want to make lightweight models that we can upload to a standalone VR HMD that is perfectly capable of doing cognitive load prediction and cybersickness prediction. We want to make an adaptive system where it can reduce cybersickness and also manage cognitive load. And to conclude, we collected a data set that actually collects data relating to your physical load, mental load, working memory, attention, and cybersickness. And participants were tasked with several different tasks that actually challenged their attention and working memory. We collected their biophysiological readings, eye tracking, head tracking, and also their POV VR images. So this is a very comprehensive data set. We collected around 61 eye tracking features, 10 head tracking features, there are heart rate, GSR, and 60 FPS VR image. So very comprehensive data set that we can actually concatenate with some of the existing other data set to make a larger data set to make the cybersickness prediction models more robust. And we also performed shape analysis to figure out some of the dominant feature. This was a way to guide the future researcher that what kind of modality you want to focus on. Like you want to focus on only eye tracking and biophysiological, because head tracking are not that important in terms of cybersickness prediction, but it might be important for cognitive load prediction, we don't know yet. So further research is needed on that as well. So to access the data, you have to go to the website of the SAVE Lab. You can request the full raw data from there. You can also visit the GitHub link or scan the QR code. It actually gives you a pre-processed version of the data that we use to predict cybersickness. But if you want the raw full data, you have to go through the first link or email me. I can set you up with the full raw link. So thank you very much.
Thank you. Is there any questions from the audience?
Hello, thank you for presentation. I'm Han from Tohoku University, Japan. And the question that I want to ask is, I saw that in your video that the participants were asked with some questions, like when they are like walking in the maze. And I'm wondering if like answering these questions is like an additional mental load to them, like make them stress, and then like add noise to your data set. Have you ever done anything to like counterbalance it or get rid of those noise?
We actually had a similar question ourselves, but when we actually designed the simulation, we still wanted the granular levels of the cognitive load, like the physical load or mental load. So that was the only way we can do that. And we still wanted FMS, so we still need to ask them 3 questions and the working memory load task. There was no shorter version that we thought of at that moment, but it definitely is a bit mentally tasking to answer those questions during the session. That's why we omit the attention task at that particular 30-second scenario, and they only do the Q&A session while they are working to reduce the mental load.
I see, yes, thank you.
Thank you for the presentation. This is Johan from Duke University. I realized that in the table you presented, there's like a coherence D at around like 20, which is really big. I guess the short question is, what makes the difference, do you think? Or like, are they just really tired at the second half? Or like, do you think this is some kind of really significant difference in the first half versus the second half of the data?
Because FMS tends to grow over time, so does physical load and so does mental load. And it will eventually grow over time. It was a 15-minute session, and we calculated based on the mean value of the first half and the second half. So there was a significant difference. And what particular value are you talking about?
I mean, I remember like a lot of coherence Ds are like 10s and 20s. Like, they're like 18.3 and 13. like these are like really big values for as for effect sizes. So like
Yeah, because we had around 40 participants data, and you have to, like, I have to go to the paper and actually figure out what kind of stat we had. There are more stats in there that will probably guide you in a better way. But there were significant difference in between their physical load, mental load, and FMS as we tested it out.
So like, do you mind if I ask about like the exact, the load that are reporting about, for example, physical at the second half? Like, are they really hard or?
Oh no, that was also in between 1 to 10 scale, because everything is like the FMS, physical load, and mental load that we collected during the Q&A session, they're all ranged between 1 to 10.
Right, so I guess my question is like, are they like kind of approaching 10 at the end of the session, or?
They are mostly tired because they are walking around the whole time, and the physical load specifically is always very up at the end of the session because they had to walk around, complete the mazes. Some of the participants were like really moving around, so they felt a little bit tired at the end. And mental load, you wouldn't see that much of a leap, but for physical load, it was a much higher difference than mental load itself, or even FMS.
I see. Yep, thank you for the answer.